So in last class, we have just formulate the concept of differential scattering cross section, and we have also learned how impact parameter is basically related to our differential scattering cross section. So the idea is all about calculating the sorry, the idea is all about calculating the relationship between impact parameter and scattering cross section. So most important thing we have to remember in the classical scattering is this is all about differential scattering cross section, and this is known as B upon sine theta dB upon d theta. And this thing is a most important thing. Once we know differential scattering cross section, we can easily talk about total scattering cross section. And this total scattering cross section is nothing but d theta d omega. And this d omega is nothing but your solid angle. You can just assume this d omega is identified as, you can have 2 pi sine theta d theta. The idea is very simple. So we have to just see what is our idea. The idea is absolutely clear. We have a basic reference line, and let us assume this is my z-axis, and we have one, we are just sending the particle, and let us assume at here we have a origin. So this is our origin, and my particle, and this potential is basically short range. So potential is here, and you can just assume this is very much short range potential is there. So this is short range potential. You can have, and here all this part you have in this all region, you have zero potential. Only you have some small region, you have some value of potential. So what will happen? The particle will come here, and it will come into influence, and again it will go into a straight line. And this particular angle is basically angle of scattering. And yes, we have to give this notation. Okay, this is your angle of scattering, that is capital theta. And this particular distance is r minimum, and this r minimum is also known as closest approach. So this is your r minimum and known as closest approach. When your particle is free, when you are sending the particle, you have to send the particle with some distance from the reference line, and this is the minimum distance, and this value is nothing but b, and that is known as impact parameter. Impact parameter. And here we can have some cross section. So this is my cross section. You can just assume there is some cross section, and let's say we can make it in this thing, and this is just a perpendicular thing. So you can just put it in a some perpendicular, just you can assume this is perpendicular into this particular board, and assume that suppose this angle, sorry, this area, if you are going to assume this area is, let's say, d sigma, and your particle is coming from this area. Suppose it is coming from this area, and it is going like this. Okay, you can have this b also, you can have another b also, you can have different type of b, you can have upper b, then you have different kind of situation. So this is your d sigma, and here you have another area you are just going to measure. Not at this point. At this point, everything is very complicated. We are measuring the thing when we are going, when my particle is again become a basically free particle. And obviously, then we are just going to measure this particular solid angle. Okay, this is your, you can just measure some solid angle, something like this. So this will be your solid angle d omega. Okay, d omega is solid angle, and this particular area is identified as differential scattering cross section. And this, if you are coming near about that, then this area will be lesser. So what we have basically this d sigma is equal to d theta upon d theta into d omega. So this is the whole story we have to understand. So sometime you can define d theta as different, then this d theta is differential scattering cross section, and this will be d sigma upon d omega, and which is also known as differential scattering cross section. The whole idea is that how you are finding d theta, and if somehow you are writing the relationship between b and theta, then obviously everything is cakewalk for you. But yes, there are different type of potential. In the last class we have talked about the potential Vr is equal to some k by r, and here we have seen that d theta is proportional to 1 upon sine to the power 4 theta by 2, isn't it? We have seen this thing in, and we have also derived this particular thing, and this is basically known as what? Rutherford scattering. Now let's try to go for some more problem based on this. So the basic physics behind that is that at this region my particle is free, in this region my particle is also free. Only in a very small region you have effect of potential. And how we can include the effect of this potential to calculation of this particular d theta is the real challenge into our all classical scattering as well as quantum mechanical scattering. And we are just sticking ourselves to central potential such that force is always in a direction of r cap. Okay, so this is direction of force, 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 and that is in r cap direction. So I can claim my total energy of a system is conserved, as well as my angular momentum of a system is conserved, and motion is in plane. Okay, motion is in plane. So these three things we have to always keep in mind when we are going to solve different types of problem. Okay, so let's try to solve different type of problem, one or two problem from classical, and then we will try to formulate the actual thing. The real thing is that how we are going to formulate the quantum mechanical scattering, and you will see that which kind of mathematics will come into picture when we are solving all this thing. And unfortunately we are not going to solve it completely. We have to solve it with some approximation method or some ideal case, or in a some ideal case. So let us try to go for that. So today I will just discuss two more problem in a classical scattering, then we will formulate quantum mechanical scattering, and at least we will reach up to a point where we can feel a real difficulty to solve the problem. And then tomorrow class we will approximate the thing such that we can at least we can give the approximated solution for scattering. Okay. So abhi tak kuch puchna hai? This is just a recap of last class, and in the last class I have given you also one picture, so that I think that will make everything clear, hai na? Because my
Yes.
drawing making capacity is not very good. Okay, so kuch puchna hai everyone?
No, sir.
Okay, so let's go for one problem. And in a classical scattering बहुत ज्यादा प्रॉब्लम नहीं आ सकते हैं, because due to compulsion of mathematical thing. Okay, so it's a very difficult. Other than Rutherford scattering, they will ask something else. Okay, and if we are lucky that we know the trajectory of Rutherford scattering, then we can solve it. Otherwise, it is also very difficult. Anyway, so in a problem, there is d sigma upon d omega is given, and this is given as, just a minute. This is in your net 2015 question. Okay, so d sigma upon d omega is given as a square plus b square cos square theta. So this is profile of d sigma upon d omega, and this will dependent on theta. And if n is the intensity of incoming particle or flux of incoming particle, intensity of incoming particle, you can, all thing are same. If I are saying intensity, flux, they are say number of particle per unit area per unit time. So n is the incoming intensity. Incoming intensity. Okay, so n is the particle, which is total number of particle per unit area per unit time is coming is n. So we have to find scattered number of particle, number of scattered particle per unit time. We have to calculate this particular thing. So how many particle will be scattered per unit time if this is profile of d sigma upon d omega? So what is this particular thing? What is this particular thing? ये क्या दिया हुआ है? This is nothing but given as what? Differential scattering cross section. So they have given the differential scattering cross section. And if we know that overall which area the particle is going to scatter, what will be the complete area where particle is going to scatter, and if we are going to multiply with this particular number n, then obviously we know how much particle is going to scatter per unit time per unit area, isn't it? This is your incoming particle per unit time per unit area, and if we know the what will be the complete scattering area, up to which area the particle is going to scatter, and if we are multiplying with the flux, then obviously we can say how much particle can be scattered with a per unit time per unit area. So what we have to calculate actually, this is very simple problem. What we have to calculate actually finally, क्या calculate करना है? Just tell me. This is given, what you have to calculate finally?
Sigma.
Actually we have to calculate n into sigma, है ना? And this is the total scattering cross section in which the effective area where the particle is going to scatter. And how you will get the sigma? The sigma can be easily find by the formula d theta sine theta d theta d phi, and this will be value of total scattering. So we can take 2 pi common, and here is a square sine theta, and you can go for 0 to pi plus b square cos square theta sine theta d theta, and 2 pi, and what will be sine theta? Sine theta is what? Minus cos theta, and 0 to 2 pi is basically 2, isn't it? And plus b square, and here is 0 to pi. What is this value? Cos square theta sine theta d theta. क्या होगा इसका value? We can put cos theta is equal to t, then sine theta d theta is dt, then you can have basically this value as 2 by 3, isn't it? जस्ट चेक कर लीजिए होगा क्या. So your total scattering cross section is 4 pi a square plus b square by 3. So this is the total scattering, and number of particle which is going to scattered. If this is incoming flux, then scattered flux is equal to nothing but n into sigma. So we have to find the scattered flux, and with that scattered flux will be scattered flux will be 4 pi n, and you have a square plus b square by 3. So this is very simple problem. So, but you have to identify what is this particular thing. This particular thing is nothing but given as what? Differential scattering cross section. Once you know this is differential scattering cross section, you can easily calculate total scattering, and then you can also calculate what will be the number of particle which is going to scattered, or flux of a particle which is going to scattered. Up to that, are you people comfortable?
Yes, sir.
पूछ सकते हो अगर आपको कहीं कुछ प्रॉब्लम है तो. Okay, let's go for next problem. Now, this is very interesting problem, and this is complete problem of scattering. Everything will come into picture. Okay, so there are some potential V as a function of R. So V is given as a function of R. So this is my potential VR, and what we have, the minimum distance or closest approach of a particle. So this will be closest approach of a particle. Closest approach is given by R. So this is your closest approach of a particle. And V is the potential. It may be some repulsive potential. Maybe you can have this potential is maybe K by R. So I am just doing it generalized thing. Okay. So this is your closest approach of a particle. What do you have to do? You have to calculate total scattering cross section. Scattering cross section. So you have to calculate total scattering cross section if E is the energy of particle. Energy of particle. So what we have to do? We have to calculate the total scattering cross section. The total scattering cross section is nothing but sigma as a function of R, E, and obviously V is also given. Then we have to use the R, capital R. We have to use all this thing. We have to calculate sigma in term of capital R. Obviously total energy have to given. Okay. So because what will be the energy, it will just tell you that it is how much fastly it is coming and how much going to penetrate this particular potential. So maybe this potential can be K by R, but I am just solving for a generalized VR. So which type of concept we are going to use? So actual thing is that we have to find the how we have to find mainly d theta. If we are able to find d theta, that will be b upon sine theta, db upon d theta. This is the main thing, but maybe sometime this d theta may be not function of theta. It may be possible that this may not be function of theta. Then obviously I have also told you that then your total scattering cross section is actually pi b square. So what is main idea? Main idea is that we have to write value of B, impact parameter, as a function of R. Or sometime they will ask the closest approach as a function of B. They may also ask this question also. Okay, so let's see what is going to happen. So obviously, let us assume there is reference line, and let's say this is my impact parameter B, and particle is coming here, and it is just going to scattered. And let us assume this is my center of potential or origin, and this distance is the closest approach. So this distance is given actually. This distance is given, and this angle is basically angle theta. Now, so initially the particle is coming with the energy E. So what will be this energy E? Is that kinetic energy or total, and is that only kinetic energy or kinetic plus potential energy? This E.
Only kinetic.
Only kinetic energy, because we have assumption that particle is free here. So obviously we can write the value of E. The value of E is equal to half mv square. So we can easily calculate the value of V is equal to 2E upon m root under. Now, what will be the angular momentum, initial angular momentum of a system? Let's say this is J. So what will be initial angular momentum of a system? So can I write the initial angular momentum of a system is equal to mvb? लिख सकते क्या?
Yes, sir.
So this is my initial angular momentum of a system, and we can write m root under 2e upon m b, and this value is equal to 2 em into b. So this is my angular momentum, and this angular momentum is conserved during the motion. In the whole places, if I have set some angular momentum, I fix that angular momentum, and that this is conserved during the whole motion. So this is very interesting. Now, can I write this angular momentum J is equal to root under 2e m b, and which is also is equal to m r square theta dot? Can I write this thing? At any particular angle, at any particular theta. Suppose I am just talking about this particular theta. Can I write this particular thing? Are you getting my point? ये लिख सकते क्या? This J, can I write this also?
Yes.
Yes, sir.
Why? Because angular momentum is conserved, and we are just solving central force problem. So from the central force problem, I have two type of velocity. At one will be some radial and another will be some tangential velocity, isn't it? At any point r, and I am taking this as my theta. Yes, are you people comfortable this thing?
Yes, sir.
Anna? Now, what will be my total energy? My total energy of a system, if I am talking about in this region, then this total energy will be divided into two parts, half m r dot square at some particular r, half m r dot square plus half m r square theta dot square. This is translation kinetic energy. This is rotation kinetic energy plus potential energy VR. Can I write this thing? Now we have to include this R minimum, closest approach. So what will be this closest approach? At R is equal to R, what is going to happen? बताइए. At R is equal to R, what is going to happen? बताओ, पढ़ चुके हैं, अब तो एग्जाम आने वाला है.
Kinetic energy will be equivalent, मतलब total energy will be equivalent to potential energy.
No, that at r is equal to r dot, sorry, at r is equal to capital R dot is equal to what? 0, because capital R is identified as turning point, है ना? Minimum distance R is identified as turning point. याद है ये सारा हम लोग कर चुके हैं नहीं? So this is your turning point at r is equal to r dot, sorry, at small r is equal to capital R dot is equal to 0. So what we have? We have a very interesting thing, that my total energy E is equal to half m r square sum theta dot square plus V capital R. And now from here I can calculate at r is equal to capital R what will be value of theta dot. So here we can use this particular thing. We can this is at the some particular r, so we can write this particular thing also, root under 2em into b can be also written as m r square theta dot I into omega. This is some different theta dot. This is some different theta dot. Okay. So I am just using the same notation. So what will be theta dot here? So I can find this particular theta dot from here. निकाल सकते हैं ना? This is the same theta dot. Okay. This is this theta dot and this theta dot is same. And this is in general. In general. Because notation कितना theta change करेंगे, that will be very difficult. So you can write some theta dot r just like this. So let us calculate, and yes, this value is known, this value is known, this r is known, then we can get the value of theta dot. So what is my theta dot is, you can have E minus VR into 2 by m r square root under. Now I can put value there, then what I will get? I will get the value of B. I will get the value of impact parameter as a function of R. We can get this particular value. So what we have B is equal to m r square upon root under 2e m, and theta dot is given by root under 2 e minus vr upon m r square. So what we have? This, so you can take this value. So this 2 is cancel. There is root m, and this root m is also cancel. We can have r outside. Let's say this is e minus vr upon e. Now look at, this is your impact parameter as a function of closest approach. And what will happen for this particular thing? What will be sigma? Sigma will be pi b square, because b is not a function of theta here. So sigma is pi b square, and you can write pi r square, and you have e minus vr by e. So ये क्वेश्चन आपके जेस्ट के एग्जाम में भी आ चुका है, इस तरह के क्वेश्चंस. ओके, सो यू कैन इजिली कैलकुलेट दिस थिंग. ठीक है. सही किया हूं मैं कैलकुलेशन में? कहीं कुछ प्रॉब्लम तो नहीं है? जस्ट चेक इट. एवरीवन कंफर्टेबल?
सर।
कुछ बोलो भाई, आप हो या नहीं हो मुझे पता नहीं चल रहा है। समझ में आ रहा है, नहीं समझ में आ रहा है? हाँ,
आ रहा है सर।
आ रहा
एग्जाम
है।
का प्रेशर ज्यादा हो गया है?
Yes, sir.
हाँ। डोंट वरी, अभी अगले 2-3 दिन में एक क्वेश्चन आपका एग्जाम में बन जाएगा, 100% गारंटी है उसकी। ठीक है, जो कराऊंगा वही आएगा एग्जाम में, डोंट वरी। सो आगे बढ़े।
यस सर।
Yes,
हाँ,
sir.
एकदम सुस्त हो रखे हो, एग्जाम के समय तो फास्ट होना चाहिए ना। बहुत ज्यादा लंबा हो गया प्रिपरेशन। हाँ, चलो, so let's come to formulation of quantum mechanical scattering, and this is really very interesting, and next 3 days we will just devote ourselves to the quantum mechanical scattering. Okay, so what is actual idea? Actual idea is very simple. What we have incoming wave. Yes, we have incoming wave. And same condition is there that my potential is short range potential. That means it will be 0 at plus infinity and minus infinity. So let us assume this is my reference line and this is my z axis. Okay. So this is my incoming wave. And obviously, incoming wave is coming in one direction. And after it is going to interact with this potential, it will just go into all possible directions. So this is the whole idea. And this is short range potential. So you can have this thing as short range potential, something like this. Okay, some short range potential. So when this particles or the beam, the wave function and the wave function associated with the particle is approaching this one, and after that, what is going to happen? After the scattering, this is scattered into all possible direction. Okay, this is going to scattered into all possible direction, and all these reason are basically there is not an influence of a particle. Only this region you have influence of a particle. So here we have also free particle. But what is your incoming wave? What is your incoming wave? It is free particle, but it is identified as what? Plane wave.
Plane wave.
So I can say it is e to the power I kz. And what are all these particles? These particles are basically e to the power I kr upon r with some amplitude, that is f theta, and you can say this is a. Okay, this is your spherical wave, spherical free particle, but your amplitude will be function of theta, because at some particular angle theta you are going to measure how many number of particle coming in this particular solid angle. Okay, this is the same story what we have done into this particular classical mechanics. So now what is my complete wave function? My complete wave function is actually something like this will be function of r theta phi, and this will be a e to the power I kz, because the complete solution is solution of incoming wave plus a scattered wave at r, and this is solution at the r tends to infinity, or at the very large r, not infinity, at the very large r, plus f theta e to the power I kr upon r, and this is at r is large. Okay, this is the solution for the large r. In general solution, you can see. Now, what is this particular f theta? This is our main question, and we have to give this particular answer. What is this particular f theta? Actual challenge is again to calculating the differential scattering cross section. If somehow you are able to calculate differential scattering cross section, then you can easily calculate the total scattering cross section. In the classical mechanics, we use the geometry and the basic equation of motion, where we can easily calculate differential scattering cross section as a function of impact parameter and scattering angle. Okay, but here we cannot apply it because we don't know the exact trajectory of a particle, because it is not classical mechanics. We can only just tell each and everything in term of probability, isn't it? Because we have associated wave function, we know the what is basic nature of wave function at the initial level and after the scattering. We know all this thing. So let us try to figure it out. What is actually this particular d theta in this particular calculation? So what we have, suppose in a unit time, and this is, suppose particle is coming freely, so it is with the constant velocity. So in a some time dt, it is traveling the distance v into dt, and this is the cross section area. Then let's say this cross section area is d sigma. So particle is crossing from this particular volume from in time dt. Okay, suppose you can just assume some cylindrical kind of thing because it is just coming into this particular thing, है ना? Just yahan se aa raha hai. Okay, so now what will be your incoming probability? What will be your incoming probability? बताइए. Incoming probability क्या होगा?
So volume of this element upon total
Obviously,
volume.
you have to multiply with mod a square into this. This is your incoming wave, है ना? Incoming wave. So you have to multiply with this volume. And what is this volume? This volume is, so this will be mod a square is your probability density into volume. Then this volume is d sigma into v dt. This is your incoming probability of a particle. And probability is nothing but the number. How much particle out of this, how much particle is coming? You cannot give guarantee that all particle is coming. So mod a square d sigma v into dt. This is your incoming particle. Now, what will be your scattered particle? So for the scattered particle, what will be your so you have, for the scattered particle, we have to write mod psi square. This is also mod psi square for incoming, so I am writing directly mod a square here. Mod psi square r square dr sin theta d theta d phi, isn't it? है ना? यही तो लिखते हैं ना?
Yes, sir.
Everyone?
Yes, sir.
Okay. Now I can write sin theta d phi as d omega. लिख सकते हैं इसे?
Yes, sir.
Okay. Now what is mod psi square? What is mod psi square? Mod psi square is
Probability density.
probability density. So mod a square
F square
mod f square
upon R square.
upon r square, and here is r square. And what is this dr? This dr is exactly same time में हम देखना चाह रहे हैं कि कितना दूर तक जा रहा है ना?
Yes, sir.
So that dr is equal to v into dt into d omega. Now the incoming probability from the same this time must be equal to scattered probability, है ना? Because probability must be always conserved. जो particle आया that have to be scattered. It is different issue that they are scattered into different direction. But number of particle is always there. Maybe it can come back. Maybe it can come back. There may be some possibility. But hence we are talking about very far away. That means we can think only those particles who are going into this direction is actually counted. So if we are just going to equate this particular thing, then what will happen? Mod A square is there, cancel out. VDT is cancel out. R square is cancel out. And what we have? We have d sigma upon d omega is nothing but f theta mod square. And what is d sigma upon d omega? What is d sigma upon d omega? The d sigma upon d omega is nothing but identified as differential scattering cross section. So if somehow, so d theta is all about mod f theta whole square into the quantum mechanical treatment. So this amplitude, and obviously I am just talking about R is very large. I am not talking about this range. I am talking about R is very large. So at this particular time when R is very large, if somehow I calculate this particular f theta, then I can easily calculate d theta. And once I can calculate d theta, then I can easily calculate total scattering cross section. And that will be d theta d omega. But calculating d theta as a function of f theta is very tedious task. It is not so simple. So what we have to do? We have two methods to calculate this one. The first method is Born approximation, and the second method is all about your partial wave analysis. And we have to learn these two methods. But before that, let us go for how we can construct the solution for the scattering. And mainly I am talking about the potential where that potential is function of R. That is mainly central potential. So this is all about the thing. The real challenge is how you are going to calculate f theta. And next 3 days, we will just try to do a lot of mathematics to calculate f theta in a different way. And this is the whole story that you have to understand in a very nice manner. So up to that, everyone is comfortable?
Sir,
Yes, sir.
बोलो.
सर हमने इसमें इनकमिंग वेव का जो वेलोसिटी था और जो स्कैटर्ड वेव का वेलोसिटी था वो हमने इक्वल माना है v
इक्वल माना है, बिल्कुल इक्वल मानेंगे क्योंकि ये फ्री पार्टिकल एंड एनर्जी इज कंजर्व.
ओके सर.
है ना? और ये भी फार अवे फ्रॉम द पोटेंशियल है और ये भी फार अवे फ्रॉम द पोटेंशियल है. तो दोनों जगह पार्टिकल फ्री पार्टिकल की तरह बिहेव कर रही है. बट इवन इफ दे आर फ्री पार्टिकल, वी हैव प्लेन वेव हियर and spherical wave here. Are you getting me this thing?
Yes, sir.
And if this is a spherical wave, then obviously this theta will come into picture because every angle you have different kind of amplitude.
Yes, sir.
है ना? And this k and this k is same because energy is conserved.
Yes, sir.
है ना? ये k ही तो वेलोसिटी बोल रहे हो तो k ही तो बात कर रहे हो. I am not writing this is k dash. Yes, this k dash will be in this region, but I cannot do anything add into this region. This is very complicated to solve that particular thing.
Yes, sir.
Okay? So let us try to go for a complete solution. How you can approach, how you can go for this. You have to understand all this story in a different man. I think this is known as form factor. If I am not wrong, this is known as form factor. That which type of potential is here, that will tell you which kind of F is there. What is this particular F, the profile of this particular F? And you will see then legendary polynomials and all these things will come into picture in a very nice way. Okay, so let's go for a formulation of complete theory of scattering. Then we will go for partial wave. What is partial wave? And then first we will go for Born approximation. Then I will go for partial wave, because Born approximation is more important for your exam point of view actually. But yes, in 3 days we will try to learn each and everything. Don't worry. I deliberately make the story such that we can do each and everything into next 3 days. And in 5 days, classical plus quantum, everything is going to cover. So, करें क्या आगे का काम?
Yes, sir.
Yes.
Okay. कोई जल्दी तो नहीं है?
No, sir.
This is very interesting. Very, very interesting. देखो, whole story क्या है? You have to define the whole region into 3 parts. One region is very dangerous one, and this region is very small region actually, and where their potential is not equal to 0. Okay, this region is identified as a scattering region. Okay, actually what we have to do, we have to solve, hence my potential is only function of R. Then you remember we have to solve this equation, minus h cut square upon 2m d square u dr square plus L into L plus 1 h cut square 2mr square plus Vr ur is equal to EUR. Okay, are you going to understand this thing? है ना? Actually, we have to solve this thing. And what is my R? RR is basically UR by R. And obviously, my psi R theta phi will be function of RR and Y LM theta phi. ये सारा तो हमें पता है ना? Because we have done all this thing into hydrogen atom. Okay? So
Yes.
now, actually, if we are enough talented, then we have to solve this thing completely and everything we can give answer. But you have seen, even in a hydrogen atom, if your potential is minus K by R, which kind of havoc we have faced, isn't it? Lot of approximation, then only after finally from the Laguerre polynomial we can get the answer. So if the potential is going to change, it is next to impossible for general people like me at least to solve this problem completely. So we make another way to solve this thing. At least we can solve approximately what kind of solution. Now, so this is your scattering region where potential is not equal to 0. This is region 2 and this is identified as intermediate region, and where your potential VR is equal to 0, but R is not very large. That means in this region into this region 2, and region 2 is identified as intermediate region. This is identified as intermediate region, where potential is equal to 0, but centrifugal term will come into picture. This will there. R is not very large. So we can say something about into this region also, because we know the exact solution at this region thanks to mathematics. And here, this particular region where VR is equal to also 0, it is very obvious, and KR is very large. KR is very large. And this region is identified as radiation region. And I am following Griffith, okay? So I am following Griffith, and I think this is the best book into this particular quantum mechanics, okay? एग्जाम के बाद आप चाहो तो एक वीडियो, एक दो क्लास वीडियो देख सकते हो. बार्टन जोविक MIT के प्रोफेसर हैं, उनके आप चाहो तो वीडियो लेक्चर्स देख सकते हो, ठीक है? बट उसके पहले बहुत ज्यादा मेहनत करनी पड़ेगी, है ना? So that is all this thing. But exam के purpose से we are doing exactly same thing what in an exam can be asked, even more than that. Okay, so don't worry about exam. After exam आप खूब try कर सकते हो. Anyway, so let's go for, so this is your reason 2 and this is your reason 1. Let's say this is your reason 1, 2 and 3. So what will happen? The particle is coming. Suppose this is my Z axis. The particle is coming here, and after then it is just going to scattered into all possible region, all in a spherical region. And we will just try to equate the continuity and all about thing into this region and this region, because we know the solution into this region, we know the solution into this region, and we will see how this region, how the effect of this region can be into this region. यहां पर पार्टिकल है, कुछ तो इफेक्ट करेगा, चेंज करेगा, कैसे करेगा, उसका इफेक्ट हम इन दोनों रीजन में एफ थीटा के लेवल पर देखने की कोशिश करेंगे. एंड वी विल ट्राई टू यूज सम अप्रोक्सीमेशन एंड वी कैन जस्ट ट्राई टू कैलकुलेट ऑल दिस थिंग. यहां तक क्लियर है ये? So let us go for reason 1. So reason 1 is very easy. So reason 1, obviously we cannot solve into reason 3. Reason 3 इसमें तो नहीं सॉल्व कर पाएंगे, because potential is there and it is very difficult to solve into this part. But yes, reason 1 and reason 2 I can have wave function. So what is for the radiation region? This is known as what? Radiation region. So in the radiation region, obviously R is very large. K is obviously constant. Don't worry about this. R is very large. So this particular, and V is also 0. So this particular term is 0. And we have a very simple equation and we know the solution. D is h square upon 2m d square u upon dr square is equal to E ur, and you have d square u upon dr square plus 2me upon h cut square ur is equal to 0. And this is nothing but my k square. Okay, at the very large distance, this is my k square. So what is value of u? ur is equal to e to the power ikr and e to the power minus ikr. So what is my radial part? The radial part is something e to the power ikr upon r, e to the power minus ikr upon r. Yes, this is the solution into this region, approximately solution, है ना? Because amplitude is always there. We will talk it later. Now, which solution you are going to accept? This one or this one? Because positive R is all going for the outgoing wave. So which one is your solution?
So first one.
First one we are going to. This will be just in the opposite direction. So no, it is not going to sink here. It is just going to something like this. Okay, something like this. Particle come, this wave function come here, and here it is going like this. So what I am going to see at the very large R, I have solution like R is equal to e to the power IKR upon R. So this is the solution into the radiation region. Let us try to go for solution into intermediate region where L part will be there. This centrifugal part will be there, but effect of potential is not there because potential is very small. So this is very important thing. So let's try to go for this. So my equation is minus h cut square upon 2m d square upon dr square plus L into L plus 1 h cut square upon 2m r square, and ur is equal to E ur. Okay, this is the equation we have to solve, and mainly we can write this equation as d square u dr square minus L into L plus 1 h cut square 2m r square must be equal to and minus k square ur. Again, k is the same thing, root under 2me upon h cut square, isn't it? है ना? The solution of this particular thing can be identified as, that is identified as spherical Bessel's function, है ना? They are be identified as spherical Bessel's function. So you can write the solution is AL, and let me write it completely. The solution is equal to AL R JL KR plus BL R NL KR. This JL and NL, its sums is identified as Bessel's function. One can be represented as sine and another can be represented as cos. So this is the solution when you have in the intermediate region. Now, after then, we will place some trick and we will introduce some new function. And that new function is identified as Hankel function, which this is just something like this thing. I am just giving you an analogy. Next day, I will solve all this thing. So I am just saying, suppose we have sine function. Then this sine function can be written as ei to the power x minus ei to the power minus x by 2i. लिख सकते ना?
Yes, sir.
And similarly, we have cos function, and this will be e to the power ix plus e to the power minus ix, है ना? Minus ix by 2. है ना? So you can write, and this function is also something like sine function and cos function. Okay, so this sine and cos function can be written as a function of exponential one, and that exponential function is something like is identified as Hankel's function. So we have two type of Hankel function, Hankel of type 1 function and Hankel of type 2 function. We will introduce all this thing into next class, and we will try to see how this f theta can be calculated. This f theta, because if you don't know what will be f theta, you cannot calculate d theta. But you will see that this approach, and tomorrow we will introduce the partial wave approach, and you will see this is one of the toughest approach. High mathematics is there, and you cannot have very satisfactory answer from there. Then obviously we will go for approximation to this solution, and that is known as what? Born approximation, where you have to use the green function into the calculation. Okay, so टुमारो वी विल कंस्ट्रक्ट बॉर्न अप्रोक्सीमेशन एंड नेक्स्ट 2 डे हम लोग सिर्फ उसके ऊपर प्रॉब्लम्स करेंगे, ठीक है? तो आज के लिए
सर
इतना
ये
ही रहने देते हैं। बताओ।
उसमें एच कट स्क्वायर बाय 2m नहीं आएगा ना एल एल प्लस 1 वाले टर्म में?
ओह सॉरी
ये
सॉरी
क्या
सॉरी,
क्या?
यस यस यस, क्या कर दिया हूं मैं, ये नहीं आएगा। तो 2m तो इधर चला गया ना। सॉरी सॉरी, यस, इसको प्लीज करेक्ट कर लो।
और u ऑफ r भी आएगा ना?
सॉरी,
और वेव फंक्शन u ऑफ r।
हाँ यू तो आएगा ही, यू तो आएगा ही। सॉरी सॉरी सॉरी, दिस विल बी आर स्क्वायर एंड दिस विल बी यू। ये तो यू तो होगा ही, सॉरी प्लीज करेक्ट इट, है ना, करेक्ट इट। सॉरी, एच कट स्क्वायर अपॉन 2m कॉमन लिया, फिर माइनस साइन आ गया, एंड दिस इज आर स्क्वायर यू माइनस के यू आर। प्लीज करेक्ट इट, है ना, करेक्ट इट। थैंक यू थैंक यू। एक्चुअली बताइए।
सर ये जो आपने स्फेरिकल बेसल फंक्शन बताया जे और ईटा,
हम्म,
ये है कॉस और साइन फंक्शंस?
सॉरी, हाँ ये कॉस और साइन का फंक्शन है, कॉस साइन की तरह ही फंक्शन है अभी। दिस इज समथिंग लाइक दैट। मैं आपको कल कुछ दे दूंगा फंक्शन, क्या होते हैं वो, ठीक है?
यस सर।
किस तरह दिखते हैं, J0 कैसा दिखेगा, J1 कैसा दिखेगा, J2 कैसा दिखेगा। यू कैन हैव साइन एंड कॉस टाइप फंक्शन, ओके?
यस
सो
सर।
बट एक्चुअली हमें किस तरह से लिखना है, हमें कुछ इस तरह से लिखने की कोशिश करनी है ताकि हम चीजों को इक्वेट कर सकें, ठीक है?
यस
सो वी विल
सर
जस्ट ट्राई टू राइट दिस थिंग। हेलो
सर क्वांटम किस तरह से तैयार कर लें सर अभी एग्जाम के लिए आगे?
क्वांटम किस तरह से तैयार करें?
जी सर, अभी सामने जो एग्जाम है उसके।
ओके, सो आई विल सजेस्ट यू जस्ट, देखो एग्जाम इज very different thing that you are getting knowledge, okay, from my point of view. Exam is all about how your attitude is towards the new problems. So वो आपका तभी हो सकता है जब आप जो आपकी प्रिपरेशन है वो बहुत ही ऑनेस्ट ढंग से करो, ठीक है? कहने का मतलब क्या है, कहने का मतलब ये है कि आप कैसे पता चलेगा कि आपका कौन सा पार्ट वीक है और कौन सा पार्ट स्ट्रांग है? कुछ तो तरीका होना चाहिए, है ना? सो उसके लिए आपको सबसे पहले तो ये देखना होगा दैट फ्रॉम द प्रीवियस ईयर क्वेश्चन हाउ मेनी क्वेश्चंस यू आर और which type of question you are feeling difficulties. Some question you are feeling very easy, some question you are going to feel average kind of thing. So first तो आप वहां से चीजों को देखना और समझना शुरू करो. And in quantum mechanics nothing to try to remember. You have concept, every topic has one individual concept. यही है ना, हर एक टॉपिक का अपना कॉन्सेप्ट है और उस कॉन्सेप्ट को आपको दिमाग में रखना है. एंड यस, पोस्टुलेट्स तो हमेशा है ही. आप क्या करो, जितने भी आपने प्रॉब्लम्स किए हैं उसमें किस किस प्रॉब्लम में किस कैलकुलेशन में आपको प्रॉब्लम होता है उसके लिए आप अलग से प्रैक्टिस करो. दिस इज माय फर्स्ट एडवाइस टू एवरीवन. समझ रहे हो ना? कहने का मतलब है कि कौन से इंटीग्रेशन में दिक्कत होती है, किस तरह के मैट्रिक्स का आइगन वैल्यू आइगन वेक्टर निकालने में प्रॉब्लम होता है, उन सबको आप अलग से प्रैक्टिस करो. और प्रीवियस ईयर के क्वेश्चंस को ऑब्जेक्टिव के पॉइंट ऑफ व्यू से मत सॉल्व करो, जस्ट ट्राई टू सॉल्व इट फ्रॉम सब्जेक्टिव पॉइंट ऑफ व्यू. कहने का मतलब यह है कि जस्ट ये मत करो कि हमारा ये आंसर आ गया, उससे कुछ नहीं होने वाला है. आप एक प्रॉब्लम लो और पूरा का पूरा सॉल्व करो और सॉल्व करने के बाद देखो कि उस चीज से क्या क्या और क्वेश्चंस आपके आ सकते हैं. आर यू गेटिंग दिस पॉइंट?
यस सर।
है ना? ये बहुत ही ज्यादा इंपॉर्टेंट है कि आपको टॉपिक के सब्जेक्टिविटी के बारे में पता हो. ऑब्जेक्टिव इज जस्ट वन पॉइंट ऑफ दैट होल कॉन्सेप्ट, है ना? तो ये चीज अपना दिमाग में रखो. और सबसे ज्यादा इंपॉर्टेंट बात है, आपको अपनी मेरिट और अपनी डिमेरिट, अपनी स्पीड पता होना चाहिए कि आप किस स्पीड से चीजों को सॉल्व कर पा रहे हो, और वही स्पीड एग्जाम में मेंटेन करना है आपको. डोंट डू इट इन हरी, हरी में कुछ भी करने की कोशिश नहीं है, जस्ट ट्राई टू सॉल्व इट एंड जस्ट ट्राई टू सॉल्व इट, दैट्स इट। बहुत ज्यादा स्ट्रेटजी बनाने की जरूरत नहीं है कि ये स्ट्रेटजी बना लिया, वो स्ट्रेटजी बना लिया, कुछ भी नहीं। हर एक दिन 10 या 15 क्वेश्चन सॉल्व करने की कोशिश करो 1 घंटे में, है ना। और जहां तक हो सके कुछ अनसॉल्व क्वेश्चन पर डे सॉल्व करो, क्वेश्चंस पेपर को फास्ट पढ़ने की कोशिश करो। दिस इज ऑल्सो वन ऑफ द बिग प्रॉब्लम जो मुझे स्टूडेंट्स के पॉइंट ऑफ व्यू से लगता है कि स्टूडेंट क्वेश्चन ही पूरा नहीं पढ़ पाता है। ऐसा होता है क्या?
जी सर।
हाँ, मुझे नहीं लग रहा है कि अगर मैं आपको 100 क्वेश्चन दूं पढ़ने के लिए तो आप 100 क्वेश्चन 3 घंटे में अच्छे से पढ़ लो और वो कंप्रिहेंड कर पाओ कि आपने क्या पढ़ा है और आप क्या समझ रहे हो। दिस इज रियल प्रॉब्लम, कंप्रिहेंशन। और एक चीज हमेशा दिमाग में रखो कि क्वेश्चन के अंदर ही आंसर पूछ रहा है, सारा चीज क्वेश्चन के अंदर ही है, उसी में आंसर छुपा हुआ है। तो थोड़ा सा आराम से स्लो प्रोसेस होकर मोटिवेटेड होकर के काम करो। सो मैं कुछ एग्जांपल लेकर के आपको बता दूंगा कि कैसे ऐसे प्रिपरेशन करना चाहिए, है ना। सो नेक्स्ट क्लास में कुछ बात कर पाएंगे अगर समय रहा तो। बट मुझे बहुत ज्यादा स्ट्रेटजिक पढ़ाई में बिलीव नहीं है, ठीक है। कि आप कोई जादू की छड़ी चल जाएगा, कोई स्ट्रेटजी बना लोगे और फिर उससे फिर आप कुछ, आई डोंट बिलीव दिस थिंग। सिंपल सी थिंग है, अगर आपको चीजें आती है तो आपसे होगा, अगर आपको चीजें नहीं आती हैं तो आपको वहां फाइट मारना होगा, और माइंड ओपन रहो वहां पर फाइट मारने के लिए, ठीक है।
सर थैंक यू सर।
90% बच्चे क्या दिक्कत करते हैं वो मैं बताता हूं, इंक्लूडिंग मैं भी स्टूडेंट रहा हूं, मेरे साथ भी ऐसा एक्सपीरियंस हुआ है। जब भी आप अननेसरी ज्यादा प्रिपरेशन करके जाते हो और आपके दिमाग में ये रहता है कि वहां जाएंगे और बस टिक करते हुए चले जाएंगे, आपका एग्जाम खराब होना ही होना है। कोई नहीं रोक सकता उस एग्जाम को खराब होने के लिए, क्योंकि आपने गलत एजम्पशन रखा हुआ है ना। एजम्पशन क्या है आपका, कि आपने एक एजम्पशन रख लिया है कि वहां जाएंगे, हमने इतनी तैयारी कर ली है, वहां जाएंगे और जस्ट टिक कर लेंगे, क्वेश्चन पढ़ेंगे टिक कर देंगे। ऐसा हो ही नहीं सकता है फिजिक्स में, फिजिक्स का किसी भी टॉपिक में नहीं हो सकता है। लेकिन आप अगर डिफरेंट माइंडसेट के साथ जाओगे, थोड़ा सा एक्साइटेड होकर के कि यार वहां जाएंगे और नए क्वेश्चंस भी मिलेंगे, कुछ पुराने क्वेश्चंस भी मिलेंगे, पुराने वाले को तो मैं फास्टली फास्टली कर लूंगा, जो नए क्वेश्चंस होंगे वहां मैं बैठ के अच्छे समय पर अटेम्प्ट करूंगा अच्छे से, विद अ फुल कॉन्फिडेंस, और सही डायरेक्शन में उसको करने की कोशिश करेंगे, तो आपका एग्जाम होने के चांसेस होंगे। क्योंकि अब आपका एग्जाम वैसा नहीं है कि फॉर्मूला आया और फॉर्मूला टिक करके चले आए। यू हैव टू डू दिस थिंग, यू हैव टू डू कैलकुलेशन, है ना। सो माइंड ओपन रखो और लर्निंग कैपेसिटी अपनी रखो कि एग्जाम के दिन भी कुछ ना कुछ सीख ही लेंगे, डोंट वरी। सो आपका फिर एग्जाम अच्छा होगा उसमें। और 3 घंटे का टाइम बहुत होता है, इट्स एनफ। मैं आपको कल बता दूंगा कि आपके पास कितना टाइम है और आपको क्या करना है, ठीक है। सो कल मैं
ओके सर।
5 मिनट का आपको बताऊंगा कि किस तरह से आपके एग्जाम का क्या पैटर्न है, कैसे अप्रोच करना चाहिए। मोस्ट ऑफ द स्टूडेंट जाते हैं और एग्जाम का पेपर पलटने लटने से, आप तो कंप्यूटर में आता है पेपर, दैट इज डिफरेंट इशू, लेकिन आप क्वेश्चन तो देख सकते हो कौन सा क्वेश्चन कहां पर है ना। लेकिन उन्हें स्टूडेंट को लगता है कि ये जो है वेस्टेज ऑफ टाइम है, और आपको पता भी नहीं चलता है कि आपने कौन सा क्वेश्चन छोड़ दिया, कौन सा क्वेश्चन पकड़ा हुआ है, ठीक है। सो प्रिपरेशन ज्यादा नहीं करना है, बट कैलकुलेशन की प्रैक्टिस और कॉन्सेप्ट को ध्यान में, रिकॉलिंग ऑफ द कॉन्सेप्ट, कॉन्सेप्ट की प्रैक्टिस, ये सारा चीज आप थोड़ा बहुत देख के जाओ, और एग्जाम के दिन फुल एनर्जी रखो कि एग्जाम के दिन अपना 100% दोगे, ठीक है। और
ओके
वैसे
सर।
कुछ स्ट्रेटजिस्ट होंगे, रोज यूट्यूब पर कहीं ना कहीं चलते रहता है, काउंसलिंग सेशन, कुछ ये कुछ वो, है ना, वो सबसे कुछ होने जाने वाला है नहीं, ठीक है। हाँ,
ठीक सर।
है ना। सो ज्यादा स्ट्रेटजी मत बनाना, ये पहला रिक्वेस्ट है, ओके। और खास के फिजिक्स में तो बिल्कुल भी नहीं। एनीवे, कल देखते हैं आगे, ठीक है।
थैंक यू सर।
Thank you, sir.